The focus of today's lecture will be on experiments. In particular, we'll discuss how to tell a good one from a bad one, the logic that goes into designing a good experiment, and finally, how to interpret the results of an experiment. After discussing all the necessary vocabulary, we will discuss potential issues when designing an experiment and how to avoid them. Just as with sample surveys, experiments are subject to variation, or variability. Statistical significance is a term that accounts for variation when presenting the results of an experiment. Finally, we discuss how to make the best of observational studies. Recall, in an experiment, we want to change responses of individuals by applying some treatment. In particular, we want to investigate the effect one variable has on another. As an example, let's consider the question, can aspirin prevent heart attacks? Here there are two variables of interest, aspirin usage and the number of heart attacks one has had. Here we want to investigate whether aspirin usage has an effect on the number of heart attacks one has had. In other words, aspirin usage is the variable we think affects the other variable, being the number of heart attacks one has had. Here we would consider the number of heart attacks to be the response variable, as it will determine whether the treatment had an effect and hence dictates the outcome of the study. Aspirin usage would be considered the explanatory variable, as it is what we think is causing the change in the response variable. Recall, the treatment is the condition applied to the individuals, sometimes called subjects, in an experiment. If an experiment has more than one explanatory variable, then our treatment will be a combination of these explanatory variables. Also, the explanatory variable is sometimes called the independent variable, and the response variable the dependent variable. Let's look at an example of a study that wanted to compare learning in online courses versus in-class courses. The authors of this study claim that students taking undergraduate courses online were equal in learning to students taking the same courses in class. Replacing college classes with websites saves colleges money, so this study seems to suggest we should all move online. College students are the subjects in this study, or the individuals. The explanatory variable considered in the study is the setting for learning, whether it be in class or online. The response variable is a student's score on a test at the end of the course. Other variables were also measured in the study, including the score on a test on the course material before the course started. Although this was not used as an explanatory variable in the study, prior knowledge of the course material might affect the response, and the authors wished to make sure that this was not the case. So do students who take a course via the web learn as well as those who take the same course in a traditional classroom? The best way to find out is to assign some students to the classroom and others to the web. That's an experiment. The Nova Southeastern University study was not an experiment because it imposed no treatment on the student subjects. So let's discuss some potential issues with the design of their study, though. Although the authors acknowledged that how prepared a student was for the course might affect their final test score, this was not considered as an explanatory variable in the study. However, let's suppose a student scores very high on the test at the end of the course. Is this because of the environment the learning took place, or due to the student being well prepared for the course? By not considering student preparation as one of the explanatory variables, it becomes difficult to determine which variable caused the change in the response, and thus weakens the results of the study. In this study, student preparation is what we would consider to be a lurking variable. A lurking variable is a variable that has an important effect on the relationship among the variables in a study, but is not one of the explanatory variables studied. Furthermore, returning to our study, the effect of student preparation is not distinguishable from the learning environment. Hence, these variables are confounded. Two variables are confounded if their effects are indistinguishable from one another. Confounded variables may be either explanatory variables or lurking variables. Now, before we discuss how to properly design an experiment, we still need a few more vocabulary terms. Experiments that study the effectiveness of medical treatments on actual patients are called clinical trials. A placebo is a dummy treatment with no active ingredients. Many patients respond favorably to any treatment, even a placebo. This response to a dummy treatment is the placebo effect. An experiment in which neither subjects nor physicians recording the symptoms know which treatment was received is called double-blind. Both observational studies and one-track experiments often yield useless data because of confounding with lurking variables. It is hard to avoid confounding when only observation is possible. To properly design an experiment, we must ensure that any change in response is due to the treatment alone. In other words, we must ensure that our explanatory variable is not confounded with any lurking variables. The easiest way to do this is to compare two or more treatments. For example, let's consider the following clinical trial, which investigated the effect a new drug has on pain for certain patients. Here, 299 patients were divided into two groups. Those in group 1 were given the drug, and those in group 2 were given a placebo. In both cases, their pain was measured. If both groups are otherwise indistinguishable, then we can measure the effectiveness of the drug by comparing the responses in both groups. Figure 5.2 illustrates the simplest randomized comparative experiment, one that compares just two treatments. The diagram outlines the essential information about the design. Random assignment to groups, one group for each treatment, the number of subjects in each group, what treatment each group gets, and the response variable we compare. The placebo group in example 4 is called the control group because comparing the treatment and control groups allows us to control the effects of lurking variables. A control group need not receive a dummy treatment such as a placebo. Let's look at an example. Many utility companies have introduced programs to encourage energy conservation amongst their customers. An electric company considers placing electronic meters in households to show what the cost would be if the electricity use at the moment continued for a month. Will meters reduce electricity use? Would cheaper methods work almost as well? The company decides to design an experiment. One cheaper approach is to give customers a chart and information about monitoring their electricity use. The experiment compares these two approaches, using a meter versus a chart, and also a control. The control group of customers receives information about energy conservation, but no help in monitoring electricity use. The response variable will be total electricity used in a year. The company finds 60 single-family residences in the same city willing to participate, so it assigns 20 residences at random to each of the three treatments. Figure 5.3 outlines the design. The randomized comparative experiment is one of the most important ideas in statistics. It is designed to allow us to draw cause and effect conclusions. Be sure you understand the logic. First is randomization. Individuals must be randomly assigned to groups. This ensures that, on average, each group is the same before the treatment is applied. Comparative design exposes all groups to similar conditions other than the treatments they receive. This ensures that additional lurking variables operate equally on all groups and thus whose effects can be ignored. Finally, when carrying out the experiment, one can conclude any change in the response is due to the treatment alone. Just as with sample surveys, experiments are always subject to the laws of chance. So, when designing an experiment, ensure that the effects of lurking variables are controlled, groups are assigned randomly. This helps remove bias in our experiment. And finally, use enough subjects. This reduces variability in our results. The presence of chance variation requires us to look more closely at the logic of randomized comparative experiments. We cannot say that any difference between the treatment group and the control group must be due to the effects of the treatments. Even if both treatments are the same, there will always be some chance differences between the individuals in the control group and those in the treatment group. Randomization eliminates just the systematic differences between the groups. However, if our results are such that they would only rarely occur by chance, then we would say that our results are statistically significant. Finally, let's return to observational studies. Although they provide less compelling results than that of an experiment, they are certainly not worthless. However, good observational studies do mimic the structure of experiments. In particular, good studies are comparative. In other words, they compare the effects of two or more explanatory variables. Good studies account for a control, and good studies measures and adjusts for the effects of confounding variables.